I'm going to show
a bit. But for first, let me just show you what this code does. Basically, what it does is it creates a new function draw dot that we can call on some root node, and then it's going to visualize it. So if we call draw dot on D, which is this final value here, that is a times b plus c, it creates something like this. So this is D, and this output node D. So that's draw dot of D. And I'm not going to go through this in complete detail. You can take a look at Graphviz and its API. Graphviz is an open source graph visualization software. And what we're doing here is we're building out this graph in Graphviz API. And you can basically see that trace is this helper function that enumerates all of the nodes and edges in the graph. So that just builds a set of all the nodes and edges. And then we iterate through all the nodes and we create special node objects for them in using dot node. And then we also create edges using dot dot edge. And the only thing that's like slightly tricky here is you'll notice that I basically add these fake nodes, which are these operation nodes. So for example, this node here is just like a plus node. And I create these special op nodes here, and I connect them accordingly. So these nodes, of course, are not actual things in squares. Those are actual value objects or representations that are. We'll add labels to these graphs just so we know what variables are where. So let's create a special underscore label, or let's just do label equals empty by default and save it. each node. And then here, we're going to do label as A. Label as B, label as C, and then let's create a special E equals A times B, and E dot label will be E. Kind of naughty. And E will be E plus C. And a D dot label will be D. Okay, so nothing really changes. I just added this new E function, a new E variable. And then here, when we are printing this, I'm going to print the label here. So this will be a %s bar. And this will be n dot label. And so now, and this will be n.label. B, D. And then here, when we are, and this we have the label. And finally, let's make this expression just one layer deeper. So D will not be the final output node. Instead, after D, we are going to create a new value object called F. We're going to start running out of variables soon. F will be negative 2.0, and its label will, of course, just be F. And then L, capital L, will be the output of our graph. And L will be D times F. Okay, so L will be negative 8 is the output. Okay, sort of given to it. There we go, so L is the output. So let's quickly recap what we've done so far. We are able to build out mathematical expressions using only plus and times so far. They are scalar valued along the way, and we can do this forward pass and build out a mathematical expression. So we have multiple inputs here, A, B, C, and F, going into a mathematical expression that produces a single output, L. And this here is visualizing the forward pass. So the output of the forward pass is negative 8. That's the value. Now, what we'd like to do next is we'd like to run backpropagation. And in backpropagation, we are going to start here at the end, and we're going to reverse and calculate a gradient along all these intermediate values. And really what we're computing for every single value here, we're going to compute the derivative of that node with respect to L. So the derivative of L with respect to L is just 1. And then we're going to derive what is the derivative of L with respect to F, with respect to D, with respect to C, with respect to E, with respect to B, its function L, with respect to the weights of a neural network. And here, derivative of basically this loss function L, with respect to the weights of a neural network. And here, of course, we have just these variables A, B, C, and F, but some of these will eventually represent the weights of a neural net. And so we'll need to know how those weights are impacting the loss function. So we'll be interested basically in the derivative of the output with respect to some of its leaf nodes. And those leaf nodes will be the weights of the neural net. And the other leaf nodes, of course, will be the data itself. But usually we will not want or use the derivative of the loss function with respect to data because the data is fixed, but the weights will be iterated on using the gradient information. So next we are going to create a variable inside the value class that maintains the derivative of L with respect to that value. And we will call this variable grad. So there's a .data and there's a self.grad, and initially it will be 0. And remember that 0 is basically means no effect. So at initialization, we're assuming that every value does not affect the output, right? Because if the gradient is 0, that means that changing this variable is not changing the loss function. So by default, we assume that the gradient is 0. And then now that we have grad and it's 0.0, we are going to be able to visualize it here after data. So here grad is 0.4f, and this will be in that grad. And now we are going to be showing both the data and the grad initialized at 0. And we are just about getting ready to calculate the backpropagation. And of course, this grad, again, as I mentioned, is representing the derivative of the output, in this case L, with respect to this value. So with respect to, so this is the derivative of L with respect to F, with respect to D, and so on. So let's now fill in those gradients and actually do backpropagation manually. So let's start filling in these gradients and start all the way at the end, as I mentioned here. First, we are interested to fill in this gradient here. So what is the derivative of L with respect to L? In other words, if I change L by a tiny amount h, how much does L change? It changes by h. So it's proportional, and therefore the derivative will be 1. We can, of course, measure these or estimate these numerical gradients numerically, just like we've seen before. So if I take this expression and I create a def LOL function here and put this here. Now, the reason I'm creating a gating function LOL here is because I don't want to pollute or mess up the global scope here. This is just kind of like a little staging area. And as you know, in Python, all of these will be local variables to this function. So I'm not changing any of the global scope here. So here, L1 will be L. And then copy pasting this expression, we're going to add a small amount h in, for example, a, right? And this would be measuring the derivative of L.
into f बचेगा a is to f is minus 2 minus b and f. Differential of this will be b and f. B is minus 3, f is minus 2, so it is 6.
L with respect to A. So here, this will be L2 is how much? L2 because L is a value divided by H, and this should print the derivative of L with respect to A because A is the one that we bumped a little bit by H. So what is the derivative of L with respect to A? It's 6. Okay, and obviously, if we change L by H, then that would be here effectively. This looks really awkward, but changing L by H, you see the derivative here is 1. That's kind of like the base case of what we are doing here. So basically, we can come up here, and we can manually set L.grad to 1. This is our manual backpropagation. L.grad is 1, and let's redraw. And we'll see that we filled in grad is 1 for L. We're now going to continue the backpropagation. So let's here look at the derivatives of L with respect to D and F. Let's do D first. So what we are interested in, if I create a markdown out here, is we'd like to know, basically we have that L is D times F, and we'd like to know what is dl by dd. What is that? And if you know your calculus, L is d times F, so what is dl by dd? It would be F. And if you don't believe me, we can also just derive it because the proof would be fairly straightforward. We go to the definition of the derivative, so 0 of this kind of expression, would give us the output of minus d times F, basically df minus, and the limit is 8, we just get dl by d now, and we see that, and so the value of f is -2. So we'll set those. Manually. Let me erase this markdown node, and then let's redraw what we have. Okay, and let's just make sure that these were correct.
With respect to f.
So we seem to think that dl by dd is -2, so let's double check. Let me erase this plus h from before. And now we want the derivative with respect to f. So let's just come here when I create f, and let's do a plus h here. And this should print the derivative of L with respect to f, so we expect to see 4. Yeah, and this is 4 up to floating point funkiness. And then dl by dd should be f, which is -2. Grad is -2. So if we, again, come here and we change d dot data plus equals h right here. So we expect, so we've added a little h, and then we see how L changed, and we expect to print -2. There we go. So we've numerically verified. What we're doing here is kind of like an inline gradient check. Gradient check is when we are deriving this like backpropagation and getting the derivative with respect to all the intermediate results, and then numerical gradient is just estimating it using small step size. Now we're going to the crux of backpropagation. So this will be the most important node to understand, because if you understand the gradient for this node, you understand all of backpropagation and all of training of neural nets, basically. So we need to derive dl by dc. In other words, the derivative of L with respect to c, because we've computed all these other gradients already. Now we're coming here and we're continuing the backpropagation manually. So we want dl by dc, and then we'll also derive dl by de. Now here's the problem. How do we derive dl by dc? We actually know the derivative of L with respect to D, so we know how L is sensitive to D. But how is L sensitive to C? So if we wiggle C, how does that impact L through D? So we know dl by dc. And we also here know how C impacts D. And so just very intuitively, if you know the impact that C is having on D and the impact that D is having on L, then you should be able to somehow put that information together to figure out how C impacts L. And indeed, this is what we can actually do. So in particular, we know, just concentrating on D first, let's look at what is the derivative basically of D with respect to C. So in other words, what is dd by dc? So here we know that D is C times C plus E. That's what we know. And now we're interested in dd by dc. If you just know your calculus again and you remember, then differentiating C plus E with respect to C, you know that that gives you 1.0. And we can also go back to the basics and derive this as the definition of a derivative. That's the first evaluation of our function, minus, just expanding this out, this will be C cancels, E minus E cancels, d by d E will be 1.0 as well. So basically the derivative of a sum expression is very simple, and this is the local derivative. So I call this the local derivative because we have the final output value all the way at the end of this graph, and we're now like a small node here, and this is a little plus node. And the little plus node doesn't know anything about the rest of the graph that it's embedded in. All it knows is that it did a plus. It took a C and an E, added them, and created a D. And this plus node also knows the local influence of C on D, or rather the derivative of D with respect to C, and it also knows the derivative of D with respect to E. But that's not what we want. That's just a local derivative. What we actually want is dl by dc. And L is here just one step away. But in the general case, this little plus node could be embedded in like a massive graph. So again, we know how L impacts D, and now we know how C and E impact D. How do we put that information together to write dl by dc? And the answer, of course, is the chain rule in calculus. And so chain rule, Wikipedia sometimes can be very confusing. Chain rule, and it was very confusing, like what is happening? It's just complicated. So I like this expression much better. If a variable z depends on a variable y, which itself depends on a variable x, then z depends on x. If you want, dz So the chain rule fundamentally is telling you how we chain these derivatives together correctly. So to differentiate through a function composition, we have to apply a multiplication of those derivatives. So that's really what chain rule is telling us. Rate of change of z with respect to y, and y relative to x allows one to calculate the instantaneous rate of change of z relative to x as a product of those two rates of change. Simply the product of those two. So here's a good one. If a car travels twice as fast as a bicycle, and the bicycle is 4 times as fast as a walking man, then the car travels at the correct thing to do, sort of, times as fast as man. Intermediate rates of change, if you will. So have a look at chain rule. But here, really what it means for us is there's a very simple recipe for deriving what we want, which is dl by dc. And what we have so far is we know want, and we know what is the impact of d on L. So we know dl by dd, the derivative of L with respect to dd. We know that that's -2. And now, because of this local reasoning that we've done here, we know dd by dc. So how does C impact D? And in particular, this is a plus node, so the local derivative is simply 1.0. It's very simple. And so the chain rule tells us that dl by dc, going through this intermediate variable to what's happening here. So we literally just have to multiply these. And because these local derivatives, like dt by dc, are just 1, we basically just copy over dl by dt, because this is just times 1. So what is the so because dl by dt is negative 2, what is dl by dc? Well, it's the local gradient 1.0 times dl by dt, which is negative 2. So literally, we're plus no.
Oh, sorry. D by dt is negative 2 net. So it will be equal to just
Node does, you can look at it that way, is it literally just routes the gradient, because the plus node's local derivatives are just 1. And so in the chain rule, 1 times dl by dt is just dl by dt. And so that derivative just gets routed to both c and to e in this case. So basically, we have that e dot grad, or let's start with c, since that's the one we looked at, is negative 2 times 1, negative 2. And in the same way, by symmetry, e dot grad will be negative 2. That's the claim. So we can set those, we can redraw, and you see how we just assign negative 2, negative 2? So this backpropagating signal, which is carrying the information of like what is the derivative of L with respect to all the intermediate nodes, we can imagine it almost like flowing backwards through the graph, and a plus node will simply distribute the derivative to all the leaf nodes, to all the children nodes of it. So this is the claim, and now let's verify it. So let me remove the plus h here from before, and now instead what we want to do is we want to increment c. So c.data will be incremented by h, and when I run this, we expect to see negative 2. Negative 2. And then, of course, for e, so e.data plus equals h, and we expect to see negative 2. Simple. So those are the derivatives of these internal nodes. And now we're going to recurse our way backwards again. And we're again going to apply the chain rule. So here we go, our second application of chain rule, and we will apply it all the way through the graph. We just happen to only have one more node remaining. We have that dl by de as we have just calculated, is -2. So we know that. So we know the derivative of L with respect to E. And now we want dl by dA, right? And the chain rule is telling us that that's just dl by dE, -2, times the local gradient. So what is the local gradient? Basically dE by dA. We have to look at that. So I'm a little times node inside a massive graph, and I only know that I did A times B, and I produced an E. So now what is dE by dA and dE by dB? That's the only thing that I sort of know about. That's my local gradient. So because we have that E is A times B, we're asking what is dE by dA? And of course we just did that here. We had a times, so I'm not going to rederive it. But if you want to differentiate this with respect to A, you'll just get B, right? The value of B, which in this case is -3.0. So basically we have that dl by dA. Well, let me just do it right here. We have that A dot grad, and we are applying chain rule here, is dl by dE, which we see here. It's the value of B, which is -3. Is again dl by dE, B, A. So these are our claimed derivatives. Let's redraw. And we see here that A dot grad turns out to be 6, because that is -2 times -3. And B dot grad is -4 times, is -2 times 2, which is -4. So those are our claims. Let's delete this and let's verify them. We have A here, A dot data plus equals H. So, and we have B dot this, all the way from here to all the leaf nodes. And we've done it piece by piece. And really all we've done is, as you saw, we iterated through all the nodes one by one and locally applied the chain rule. We always know what is the derivative of L with respect to this little output. And then we look at how this output was produced. This output was produced through some operation, and we have the pointers to the children nodes of this operation. And so in this little operation, we know what the local derivatives are, and we just multiply them onto the derivative always. So we just go through and recursively multiply on the local derivatives. And that's what backpropagation is. It's just a recursive application of chain rule backwards through the computation graph. Let's see this power in action just very briefly. What we're going to do is we're going to nudge our inputs to try to make L go up. So in particular, what we're doing is we want A dot data, we're going to change it. And if we want L to go up, that means we just have to go in the direction of the gradient. So A should increase in the direction of gradient by like some small step amount. This is the step size. And we don't just want this. For B, but also for B nodes, which we usually have control over. And if we nudge in direction of the gradient, we expect a positive influence on L. So we expect L to go up positively. So it should become less negative. It should go up to say forward pass. So let me just do that here. This would be the forward pass. F would be unchanged. This is effectively the forward pass. And now if we print L.data, we expect, because we nudged all the values, all the inputs in the direction of gradient, we expect a less negative L. We expect it to go up. So maybe it's -6 or so. Let's see what happens. Okay, -7. And this is basically one step of an optimization that will end up running. And really, this gradient just gives us some power because we know how to influence the final outcome. And this will be extremely useful for training neural nets, as we'll soon see. So now I would like to do one more example of manual backpropagation using a bit more complex and useful example. We are going to backpropagate through a neuron. So we want to eventually build out neural networks. And in the simplest case, these are multilayer perceptrons, as they're called. So this is a two.
Introduced. Is supposed to.
Two-layer neural net, and it's got these. Using a bit more complex and useful example, we are going to backpropagate through a neuron. So we want to eventually build out neural networks. And in the simplest case, these are multilayer perceptrons, as they're called. So this is a two-layer neural net, and it's got these hidden layers made up of neurons, and these neurons are fully connected to each other. Now, biologically, neurons are very complicated devices, but we have very simple mathematical models of them. And so this is a very simple mathematical model of a neuron. You have some inputs, X's, and then you have these synapses that have weights on them. So the W's are weights. And then the synapse interacts with the input to this neuron multiplicatively. So what flows to the cell body of this neuron is W times X. But there's multiple inputs, so there's many W times X's flowing into the cell body. The cell body then has also like some bias. So this is kind of like the innate sort of trigger happiness of this neuron. So this bias can make it a bit more trigger happy or a bit less trigger happy, regardless of the input. But basically, we're taking all the W times X of all the inputs, adding the bias, and then we take it through an activation function. And this activation function is usually some kind of a squashing function, like a sigmoid or tanh or something like that. So as an example, we're going to use the tanh in this example. NumPy has a np.tanh, so we can call it on a range, and we can plot it. This is the tanh function, and you see that the inputs, as they come in, get squashed on the y-coordinate here. So right at 0, we're going to get exactly 0, and then as you go more positive in the input, then you'll see that the function will only go up to 1 and then plateau out. And so if you pass in very positive inputs, we're going to cap it smoothly at 1, and on the negative side, we're going to cap it smoothly to -1. So that's tanh, and that's the squashing function or an activation function. And what comes out of this neuron is just the activation function applied to the dot product of the weights and the inputs. So let's write one out. I'm going to copy paste because I don't want to type too much. But okay, so here we have the inputs, x1, x2. So this is a two-dimensional neuron. So two inputs are going to come in. These are thought of as the weights of this neuron, weights W1, W2. And these weights, again, are the synaptic strengths for each input. And this is the bias of the neuron, B. And now what we want to do is, according to this model, we need to multiply x1 times W1 and x2 times W2, and then we need to add bias on top of it. And it gets a little messy here, but all we are trying to do is x1 W1 plus x2 W2 plus B. And these are multiplied here. Except I'm doing it in small steps so that we actually have pointers to all these intermediate nodes. So we have x1 W1 variable, x2 W2 variable, and I'm also labeling them. So N is now the cell body raw activation without the activation function for now. And this should be enough to basically plot it. So draw dot of N gives us x1 times W1, x2 times W2 being added. Then the bias gets added on top of this. And this N is this sum. So we're now going to take it through an activation function. And let's say we use the 10H so that we produce the output. So what we'd like to do here is we'd like to do the output, and I'll call it O, is N dot 10H. Okay, but we haven't yet written the 10H. Now, the reason that we need to implement another 10H function here is that 10H is a hyperbolic function, and we've only so far implemented a plus and a times, and you can't make a 10H out of just pluses and times. You also need exponentiation. So 10H is this kind of a formula here. You can use either one of these, and you see that there's exponentiation involved, which we have not implemented yet for our low value node here. So we're not going to be able to produce 10H yet, and we have to go back up and implement something like it. Now, one option here is we could actually implement exponentiation, right? And we could return the exp of a value instead of a 10H of a value. Because if we have exp, then we have everything else that we need. So because we know how to add and we know how to add and we know how to multiply, so we'd be able to create 10H if we knew how to exp. But for the purposes of this example, I specifically wanted to show you that we don't necessarily need to have the most atomic pieces in this value object. We can actually create functions at arbitrary points of abstraction. They can be complicated functions, but they can be also very, very simple functions like a plus. And it's totally up to us. The only thing that matters is that we know how to differentiate through any one function. So we take some inputs and we make an output. The only thing that matters can be arbitrarily complex function, as long as you know how to create the local derivative. If you know the local derivative of how the inputs impact the output, then that's all you need. So we're going to cluster up all of this expression, and we're not going to break it down to its atomic pieces. We're just going to directly implement 10H. So let's do that. Def 10H. And then out will be a value of, and we need this expression here. So let me actually copy paste. Let's grab n, which is a cell.theta, and then this, I believe, is the 10H. Math.x of n minus 1 over 2n plus 1. Maybe I can call this x, just so that it matches exactly. Okay, and now this will be t, and children of this node, there's just one child, and I'm wrapping it in a tuple, so this is a tuple of one object, just self, and here the name of this operation will be 10H, and we're going to return that. Okay, so now value should be implementing 10H, and now we can scroll all the way down here, and we can actually do n.10H, and that's going to return the 10H output of n. And now we should be able to draw it out of O, not of N. So let's see how that worked. There we go. N went through 10H.
next one. Then you get that. Okay. Then कल implement करेंगे.